science like there's no tomorrow.
Hi, welcome everyone after the break. Today we will continue with the second block of lecture number 2 of financial engineering course for pricing and of interest rates and XVA. Last lecture we discussed the concept of filtration, conditional expectations. We also went through the code of conditional expectations and exercise and simulation in Python. Today we will go into conditional expectations and will be much more advanced experiment that we have performed previously. So now we will actually focus on option pricing and using the tools from conditional expectation to really facilitate improved convergence in the Monte Carlo simulation. I will also introduce you to the concept of Numeraire and what is the Numeraire, how to look at it, how to use it, and how useful it is in derivative pricing. And also in this block, we will use the concept of Numeraire and also the Grzelak theorem to the Black-Scholes model, where we will change the dynamics from the the real-world measure from measure P. We will change the dynamics of the Black-Scholes model to measure Q. So it will be geometric Brownian motion, our underlying process, and we will change the measure. Typically, once we talk about the P and Q, we always associate those measures with, in the case of P, it is historical measure based, where parameters are based on, let's say, historical observations, some sampling. Once we talk about Q, it is typically associated with derivative pricing. So in the second block, so the first block was filtration, simple conditional expectations. Second block is about conditional expectations and measure changes. And in the third block, we will concentrate on detailed measure changes. I will show you multiple advantages and tricks how to use measure changes for some reductions in dimensions and how to really benefit from that. But now let's focus on the following 4 elements of today's lecture. Enjoy. Now we will use the knowledge about the conditional expectation and filtration to real option pricing. So we will take an option, a European type of option, and we will see how this can be used, the expectation of a Tower property of expectation for pricing, once we consider stochastic differential equations of much more involved form that we had for Black-Scholes. So for that reason, we will have chosen here a stochastic differential equation, which resembles the Black-Scholes model. However, volatility is not sigma, which is constant, but volatility is stochastic. So in this case, J, it is some normal distribution with some mu and sigma squared. So you see that there is some stochasticity in the variance, in the volatility. So it is not anymore as trivial as for Black-Scholes. For Black-Scholes, the derivation of Black-Scholes model relies on the assumption that J or sigma is deterministic. Actually, the Black-Scholes model is derived for constant sigma. However, we can also generalize the model to have it for time dependent. However, for stochastic case of volatility, Black-Scholes formula doesn't work, so it's not derived. So now what we are going to do is we are going to use the expectation, the Tower property of expectation, to essentially solve this problem and also improving our Monte Carlo simulation. So we will, of course, now at this point we could just simulate paths. We could randomly sample J, which is follows normal distribution, and we could say, okay, this gives you a price for an option. That, of course, that would be a valid statement. However, by using the conditional expectation, and this will be shown in a few slides, can strongly and really significantly improve the convergence of the Monte Carlo, and can also reduce the number of Monte Carlo paths that you need to have in order to achieve satisfactory convergence, satisfactory results, the stable results, you can say like that. So you see that this is introduction, let's say, to the real case. In practice, also what we have learned from the computational finance course, and this volatility part would be not in terms of a random variable, it would be a process. Yeah? That's typically what we have in finance. parameters could be stochastic, but typically they're associated with their index with time. They're associated with stochastic differential equations. But this is just a simplistic example to illustrate the powerfulness of the power of the conditional expectation. So if we just solve this equation, so this is using Ito's lemma, the solution, it is just like we would have it for Black-Scholes case. We have half j squared. Black-Scholes case, we can also, it's just as we would have it for sigma. So we have a st equals s0 exponent. We have a correction squared sigma squared, so it's a half of sigma squared times time. And then we have a Brownian motion at the maturity times j, and j here it is still stochastic. So you see, actually, when we want to find the solution for this SD using Ito's lemma, it doesn't really matter whether j is constant or it is a random variable. Actually, the solution will be always of the same form. Okay, so what we are going to do, we are going to apply iterative expectations, as just mentioned, for pricing of European options. So this is European payoff. I have on purpose removed here the discounting. This will be actually, at the end of this lecture, extension to discounting will be given as a homework. So here we have a case where we have a European call option with a maximum st minus k, and that can be written. So what the plan is actually, the plan is that because we know that j is a stochastic, and we know that if for a simple case where we have a constant j, let's say sigma, then we can use Black-Scholes model. So the idea would be to condition expectation for a call option price on a j. Then because then for each realization of j, we can simply apply Black-Scholes pricing formula. So this is what happens here. So we have a tower property, we have an outer expectation, and we have an inner expectation. So you see inner expectation, we do maximum st minus k. This is just as we was here. However, we condition j is equal to small j. This inner expectation basically means that if we look at the solution of our stock, this would be just small j. And small j, it would mean that it's just a simple realization. It's the same here. This is just a one sample from j. So it's not stochastic anymore because we conditioned on j. Conditioning on j basically means we give it as a constant input. And of course, in the outer expectation, we will sample from j and then pick up each individual j through this and plug into this pricing equation. So we see this inner expectation here, because we have conditioned on particular realization of j, this is just a Black-Scholes formula. However, the outer expectation requires that we need to still sample, get samples for j, and then for each sample we get the Black-Scholes formula. So if we look at the solution, so as just mentioned, if we have a conditional expectation, then stock process will be just as we had in the previous slide, except instead of capital J, which represented a random variable, we have a small j, which is just a realization. And then this is the same, so we see just a Brownian motion, time in. Of course, t0 equal to 0 essentially would mean that we have just 0 here. This would be gone, also gone, right? So it is just maybe longer expression of the same thing. And of course, now using the Black-Scholes formula, because we have conditioned on j, then simply this inner expectation is just the call option price for sigma equal to j, or j equal to j, realization, which is simply Black-Scholes formula. But you see now in this Black-Scholes formula, what is important to note is that we don't have sigma anymore. We have a j, which is actually comes from this conditioning. So the Black-Scholes formula essentially is deterministic. However, it has to be sampled for different j's, and then we have to revalue. It's the same here for j, and also we have a one sample here for j. And of course, now if we have this, if we use this expression, so if we use this expression here, the analytical expression in terms of Black-Scholes model, what we can do, we have to plug it in to this outer expectation. So we have this outer expectation and this inner expectation. We can substitute with exact given j is equal to j. This is what we do here. So this will be our exact representation for each realization, and then we plug it into this outer expectation, and then we have obviously we have expectation, and that is this inner expectation we have just solved. Many things can go outside the expectation, and then we simply have two terms. So we have expectation of a normal CDF of D1. D1, keep in mind, it would still depend on J. So this is not deterministic. It is still stochastic quantity. So this distribution, the CDF, it is CDF, which has a parameter which is stochastic. And it's the same for this quantity. We have D2, and it's the same quantity. It is still stochastic because one of the elements there is J, which is stochastic. And so this is this part. And of course, now you can ask, what are the benefits of the conditional expectation if we still need to perform a simulation? Obviously, those two expectations, you still need to compute them. So in order to compute them, you need to get samples for J. And of course, the maybe non-trivial answer is that because we know that inner expectation conditioned on each individual path is Black-Scholes, this basically means that our Monte Carlo simulation, a lot of uncertainty related to that relation is extracted, can be removed, because essentially we just part which would be also stochastic, we have substituted with a Black-Scholes formula. So this means if you think of a randomness, we have some space of randomness, random choices, and some information about the model used in pricing we have provided to that engine. So this means that the randomness, the scope of random choices is much limited because we gave the engine, our Monte Carlo engine, information that some elements of our simulation we know. And of course, if you are looking for a solution and I can provide you with some boundary conditions, obviously that will reduce the scope where you have to search. And this is the same case here in Monte Carlo simulation, because we provided this solution, some part of the solution that will help achieving better convergence. And that will be very clear in next slide, because next block we will go into Python simulation, where we will take this exercise, this example, we will simulate with Monte Carlo with two cases. So the brute force approach, where we sample just directly the expectation without using knowledge about the Black-Scholes relation. And then we compare to this expression where we take expectation from results obtained from the Black-Scholes model. If you're interested more about the practical aspects of conditional expectations, then I would refer to the book. We have two elements which are quite nice in a section, chapter 3 and chapter 12. Chapter 3 is about stochastic volatility, how to extend what we have just discussed to stochastic volatility. And in chapter 12, the tower property is used for pricing of couplets. Now is the moment where we would like to quantify the impact of applying of tower property for expectations in Monte Carlo simulation. So as we have just discussed, in order to price this model, Black-Scholes model with jobs, so random variable for volatility, we have two options. We can either choose brute force Monte Carlo simulation, where we say, okay, we would like to just simulate, and we take expectation for call or put option, then we get the price. However, on the other hand, we have used a lot of information about the conditional expectation, about the relation to the Black-Scholes model. Let us see now what is the impact, how much convergence gain we can get from this kind of application. So this is a figure I have prepared here. So this is on the x-axis, we see number of paths. So number of Monte Carlo paths. So this is increasing up to 20,000 Monte Carlo paths. On the y-axis, we have an option. I consider only one strike. So we have only a call option with a given strike and the money strike. So this is ATM. The orange line shows us the convergence for the case where we have used the conditional expectation approach. So we have this hybrid approach where we use some information about the relation of conditional expectation and the Black-Scholes model. And the blue line represents the case where we used brute force. So this means we haven't used any information about the Black-Scholes model. We have simply sampled the stock and evaluated expectation related to the payoff, so related to the call option in this case. You see the difference is huge. Yeah? So even for a low number of Monte Carlo paths, the results are very stable. and they are oscillating around the same number, the same points. Of course, this can be further enhanced once we will use, for example, smaller time steps in a Monte Carlo simulation, because here we have just used Euler scheme. So we know from the course of computational finance that this kind of scheme would have some error related to the time step. So this is, of course, also represented in these values here. However, you can see that for the blue line, for Monte Carlo brute force, there is a huge oscillations and it slowly converges. Of course, now we can also extend number of Monte Carlo paths from 20,000 to 100,000 and see this phenomena better. But you can see here that it's very narrow bandwidth here with a narrow band for the uncertainties. Here it is more of this shape, right? So you see there's a huge gain in terms of Monte Carlo simulation that we can gain, or we can reduce the computational cost if we would use the nested expectation. Let's take a look at the Python code, how to perform this type of simulation. So the simulation Monte Carlo code consists of few parts. The first part is where we generate Monte Carlo samples for the stock. So here we have, just like for Brownian motion, we have a Z matrix and we have a J. J is the volatility. In this case, it's just also a random vector, actually a random variable sampled from the normal distribution, some parameter mu j and sigma j. And then we perform here Euler discretization, where sigma, or we just used Euler discretization using j. So this is the Monte Carlo path, Monte Carlo part. And here we also have a part where we just calculate the pay. So given the paths, we use the expectation, we call our put option, we take expectation at the maturity. Of course, this part of the code does not really know whether at which point we take expectation, so at which point, that point. So in this case, you have to make sure that you always incorporate the last column of the matrix S, because matrix S, it's a columns that represent the time, and the y-axis or the rows correspond to path. So as the input, you have to always make sure that you use the last column. Of course, in production, if you use it for real pricing derivatives, you would make sure that everything is nicely consistent and you cannot make this mistake. However, be careful if you just put here whole matrix S, so for every time step, this maximum and this mean will be taken for all the paths. So then you can really have a big mistake, big error in the simulation. Here we see a Black-Scholes formula. So this is just a Black-Scholes equation for calls and puts. This is, we already have seen it in the course of computational finance. And here is the conditional expectation part. So where we use for each sample of J, where we will use the Black-Scholes equation. So you see that what we do here, we take the last column of J. So this is the column at time, the final time step. And we take sigma, which is each path. So we iterate over all the paths for J, and we calculate the Black-Scholes equation for sigma, which is sigma is the realization of the volatility. You can see it is simply incorporated there. And then we have this is from t to t, so this is 0 to the maturity until maturity. And what we do next, we take the expectation of all those results. And here's the main file where we take the initial point. This is the maturity of the expire of our option. We have mu j, so this is the expected volatility, you can say, for Black-Scholes model. And we have also some uncertainty. Be careful in this simulation here if the volatility here will be large. You may also encounter a simulation where volatility for Black-Scholes model would be negative. Then you have to make some adjustment to your Black-Scholes formula for that particular case. So this is why I kept it not so big, kind of in a range that we can see the illustration of the efficiency without going into the details on the fixing of the particular case when the volatility becomes negative. Here we simulate the paths, and then we generate some plots for paths. And here is the core point. So we specify an option. So this is K80. Here we had stock of 100. We have a call option. And this part is just a reference. It's not so important here. And what we do next, we iterate over number of paths. So we see we have n grid. And n grid is the range from 100 up to 20,000 for 1000 time step, and we can actually make here 10,000 faster a bit because we don't need so many simulations. And then for every path, so we see not maybe every path, for every set of paths, because we see n will vary from 100 until 10,000 with step of 1,000. We perform Monte Carlo simulation. We evaluate brute force approach, where we evaluate option price given the stock at the maturity, and then for a vector, actually for matrix J, we evaluate conditional expectations. So the pricing, which was defined here, where we take for each realization of J, we take Black-Scholes formula and evaluate the price, and we take the expectation. So this is basically the whole code. And let's run it. So the first graph shows us, of course, first two graphs. So this is the process for X. Here we have process for S. Here, the most important, of course, is the performance, the convergence of the price. So we see that the reference value would be somewhere around 35. The orange one, the conditional expectation, is very, very stable. It doesn't really change so much depending on number of paths. And the blue line, it is, especially in the beginning, before we go to 2,000 paths, is highly volatile. However, you can also see that for 6,000 paths, the results are still, you can be significantly off. And this has to do with the jumps. So of course, the blue line, the blue simulation, does not really take the advantage of properties we have used in the simulation for the conditional expectation. And that's the big disadvantage of this approach. So whenever you have a simulation in which you can incorporate some external information that you know about your model, for example, information about moments, information about some particular cases, that will always facilitate and help in your Monte Carlo simulation. Well, of course, the question is how to use this information so that your simulation is still unbiased. This will be maybe a topic for in the next course, because of course you can also make some mistakes in that. And so if you have external information which is imposed on the wrongly simulated paths, that may lead you to bigger issues than you had. Imagine a scenario where you simulated Monte Carlo, but you had a bug in your Monte Carlo paths. So the paths were always with different volatility than you expected. However, because you impose some properties, your results might look better than actually they would look before you have included this extra information. So what is important is that first you should always brute force approach as your reference, and then include extra features to see improvement going from that point. But if you don't have brute force approach, you are exposing yourself to a risk that the results you are seeing, they're not really good, and actually there could be also a bug that you may not find. I hope this code is clear. Of course, it will be also available on the website. Knowing how to operate with filtrations, expectations, conditional expectations, and Tower property for expectations, it allowed us already to significantly improve our Monte Carlo simulation and also, of course, pricing in general. Another technique which is very important, and I would say this is the core of today's lecture, is the concept of measured changes, which can actually help us even further in derivative pricing, especially once we talk about interest rates, which is the class of products which is considered to be one of the most difficult ones if we compare to stocks, FX, for example. Interest rates require much more advanced tools compared to other asset classes, and measure changes is the integral part of that tool set. So maybe in your courses you have seen measure changes, you have applied that. In this part, we really concentrate on how to use it, how to consider as a tool, and how to be handy with it. So I will show you tips and tricks, and also how to really get this concept of measure change and how to really apply it. This is the objective of this block. Change of measure is associated with the concept of Numeraire. So this is something that it's an integral part of the measure changes. When dealing with involved system SDEs, it is sometimes possible to reduce the complexity of the pricing problem by appropriate measure transformation, especially in the world of interest rates when we have multiple underlying, for example, rates of different frequencies, like for example, LIBOR 3 months, 6 months, and so on. In order to link them together, to have one consistent framework, we really rely on the measure transformation, which allows us to bring the stochastic processes from different measures into one underlying measure. Of course, maybe this right now, this concept of different measures, it's a little bit maybe sounds very complicated. But I hope that in this course you will learn and get very handy how to operate with those very important and handy tools. In financial finance, or in finance in general, mathematical finance, Numeraire is always considered to be a tradable entity in terms of whose price of relative prices of all other tradables are expressed. So this means that if you have a basket of assets, you could say you have apples. In this case, you can say apples, pears, some other things. You express the value of them in terms of one of the assets you have in your basket. So, for example, you can express all sorts of prices of all your products in terms of apple. Then apple would be considered a Numeraire. So, for example, you want to buy a television set or something else, and then you express a price in apples. That apple would be considered Numeraire. Everything else would be a Numeraire. So everything would be expressed also to that Numeraire. And then you have a, let's say, consistent way of transferring goods and services between different counterparties. So then once you express the price in a particular asset, like apples or bonds or stocks or money savings account even, then you have a consistent framework where we know everyone in this market knows what is the value of it, because it refers to a particular asset that those values are expressed in. So this is very intuitive concept, so you can say. Yeah? So, for example, in the past, values of products were expressed in amount of gold, for example. Then gold was considered to be Numeraire. In many other years, and of course over the centuries, the Numeraires have changed, but the tools of expressing assets in some particular Numeraires, this is something that we apply in financial engineering, because it happens that it is sometimes, if you have a proper choice or smart choice of Numeraire, it can significantly improve your complexity, and actually you can reduce your complexity. It can improve your simulation. It is a very handy tool, and in this lecture you will see how you can benefit from that aspect. Under the appropriate Numeraire, the process may become martingale. And this is something which connects measures, Numeraires, and processes, because typically like to work with martingales, because martingale is a process which does not have a drift. And as we already have seen before, processes without drift, those are typically easier to deal with than processes with drift, especially if you have stocks, you have a stochastic interest rates. Then you see that if you have a stock and stochastic interest rates, so for example, if you have a dynamics of a stock, DST is equal to RT ST dt, then we have also some volatility here, ST dWt. So if we have RT, so interest rate for a stock, which is constant, then we can just simply use Black-Scholes formula if you would like to price call and put options. However, if interest rate is stochastic, and for example follows certain process, then it becomes much more complicated problem, because then we have to deal with the two dimensions, because there is a relation between there is a correlation between interest rates and stocks. So this means that you see that in this case, the problem becomes two-dimensional, because we have interest rates, we have stocks, and there's a correlation between the two. However, with measure changes, we can actually reduce this problem. You can actually, in essence, in this problem, we can remove the drift by proper measure changes. And as you can see, if we are able to remove the drift, then we have something that we are already familiar with. We already know how to deal with processes without drift, because that would be just a Black-Scholes formula without interest rates. And of course, the question is what is the mechanics behind that we are allowed to remove the drift? And that is related to the concept of measure changes in Numeraire. Of course, you cannot always change the measure such that processes will become driftless. Sometimes it's much more involved. Often, it also happens that if you are even able to remove the drift, the process for the dynamics for your variance, because this is not always constant, could be so complicated that you're still not able to solve this problem. However, in general, once you have removed the drift, typically the problem becomes simpler, not more difficult. So, of course, working with, like I just mentioned, working with martingales is typically favorable to these processes as we have drift-free stochastic differential equations. And as I just mentioned, that if we have driftless processes, it doesn't mean always that the problem is solved. So this is also, please keep that in mind. Possible numeraires, so this is also an interesting question. You can think of assets that you can buy or sell. You can have money savings accounts, you can have bonds, you can have, for example, stocks, and many other assets. And often the question is Bitcoin a numeraire? And the answer depends on how we define Bitcoin. Is a Bitcoin a currency, or is a Bitcoin a commodity? If it's commodity, we can immediately say yes, it is could be a numeraire because we could express values of other assets in Bitcoin. However, if you think of FX or it's a cross currency, the foreign exchange element, then FX in general is not a numeraire. So this is something to keep in mind. Numeraires are, if you look at the FX rate, it's not a numeraire. Numeraire is something which you can buy and sell. We cannot buy FX. We can exchange euros to zloty or to dollars to euros, but we cannot trade exchange rate itself. So exchange rate is a tool. In this course, we will learn also how to look at the foreign exchange measure changes. What are actually numeraires there? But in Bitcoin in general, if it's considered to be a commodity, then as any other asset, you could consider to be numeraire. From some people, there's some criticism of Bitcoin being a numeraire, but this is outside the scope of this course. So when we talk about measure changes, when we talk about tradable assets, we always talk about measure which is associated with particular dynamics of the process. So you can see here we have three different cases. So these are the most common cases where we have tradable assets used as numeraire. In the first case, which is the most common, especially if you are talking about stocks, then we have a numeraire, which is the money savings account. You see, it's MT, and MT is simply defined as the DMT is equal to RT MT. And that's typically called a risk-neutral measure. So once we talk about risk-neutral measure, then typically the measure associated or numeraire associated with the measure, it is a money savings account defined in that way. And then we can say, okay, we have a process which we have here, of course, Brownian motion has this Q here, which corresponds to, of course, this expectation Q corresponds to this Brownian motion measure, and that corresponds to numeraire. So whenever you see a process, you can see WQ. This is typically associated with the measure that we are working under. And this also indicates you that if you have such a process, what quantities in this asset, in this world, are martingales. So if, for example, you have this dynamics and you see Q, you see it's okay, this is associated with the money savings account, this means that every asset in that world divided by money savings account divided by MT has to be martingale. So this means expectation of XT over MT is equal to XT0 MT0. This is something also I mentioned in a computational finance course. Once you perform Monte Carlo simulation, for example, of a process of this form, always make sure, always double check whether this quantity holds. Because if this doesn't hold, this means you have a bug in your code. Typically, the process because by definition this has to hold. So if simulation of this process doesn't bring you this equality, then typically you have a problem if you code. And that's first thing to check once you are busy with simulating of stochastic differential equations. Another measure, also more important than in an interest rate world than in a stock world, is a measure associated with a zero coupon bond. Zero coupon bond is a derivative which pays exactly 1 unit at the maturity time t. Later in the slides, we will go into more details about zero coupon bonds and how it is defined, but this is just a simple contract that you buy today, typically below 1. And at the maturity of the contract, which is at capital time t, you get 1. So essentially, you can say it's a time. Here we have t, it could be today. Then we have t, we receive $1, and we pay less than $1. And basically, there is only one payment which happens at the maturity of this contract. Of course, this could be, of course, here could be also higher than 1. This is also very funny because typically we had a case where it wasn't the case that it's that the bond can be higher than 1. But if you have interest rates that can be negative, you can actually have a situation when you can buy a bond for more than €1 and receive euro at the end. So that's maybe you can consider this weird. Who would buy such a bond? But this is also something which happens in the market. It's also a reality already for many years. So if we have a zero coupon bond, with that zero coupon bond is associated with the, you see there's a maturity time t. So when you get this €1 or $1 back, and that's associated with a t forward measure. So this t here, it is linked to this t by the expectation, and that is also related to this t here. So if we see a process under with a t, this means that all the quantities in this market that have the same t, they are martingales under that measure. So zero coupon bond is a numeraire. This means expectation under that measure corresponding to this maturity. It is all the assets after the martingales. So this means we have just xt0, pt0, t. This is also you see the same case as we have seen here in this case. So that's nothing special. The most important is, of course, is the consistency. And of course, the question is how to change one measure to another one. It's also very important. That's linked to the measure change concept. We can also have a stock as a numeraire, which is, as you will see in a few slides, that how stock being a numeraire, it's really sometimes very helpful in solving problems that seem to be very advanced and very involved with a very, very simple way. In stock, as before, we have a stock to be a numeraire, so we have an expectation of S, dynamics of a process under this measure. Every asset in that world discounted with ST is basically margin. So you can say discounting with the money savings accounts. Here we kind of discounting with the zero coupon bond. Here we discounting with S. Sometimes, of course, we are used to have a discounting when we say it's a money savings account, so we have just a discount rate. But if you go into more advanced mathematics and financial engineering, concept of discounting changes its meaning. Then you use it according to the measure that you're working with. However, there is a consistency. So this means that if you have this process, and if you change it to the t forward measure, it doesn't really matter because you still all these quantities. By changing measure, you are not losing any properties of the processes. Change of measure is only used to benefit the benefit from the processes and properties that change of measure allows you to. So this is the essence. Keep that in mind. Q is always risk neutral. T is a t forward measure. S is stock. Sometimes S will be also indicated by zero coupon bond maturity with S. But in this lecture series, I will explicitly mention what type of asset is used as a numeraire. And FX is not a martingale, is not a numeraire, because you cannot retrade it. You can trade assets from different currencies and then exchange them with FX rate. But that will be also covered later. Very important tool that is used for market measure changes is the Girsanov theorem. Girsanov theorem, it allows us to switch from one measure to another. For many of you, it may seem a little bit maybe advanced and complicated because it essentially states what are the measure change principles you should use to switch from measure A to measure B. And that can be done, of course, under certain conditions. You can read in the book. The measure transformation is done in the following way. Here, I would like to concentrate mainly on the practical aspects. So the concept of Girsanov theorem, really diving into the theory, is outside of the scope of the course, because here I would like to just focus on how to apply this theory and theorem to real problems and how to extract the essence of the technology, of the method, to define processes as martingales and measure change as a tool to get. If you like to go into details on the measure changes in Gears and of theorem, I recommend to go into the book and also look at the exercises defined in the book. What is the most important takeaway from the Gears of theorem is that if you have a measure A and you like to change the numeraire from A to B, so you like to change from QA to QB, by using the following measure transformation, so using the following Nikodym derivative, which is q dqb dqa with an exponent, and we have something like you could see in Black-Scholes case, which is basically integral. If it's an epoch correction, you can say half minus half integral from 0 to t y squared s ds. And then we have the Brownian motion. Then you have the following measure transformation of the Brownian motions, which allows you to switch to find the dynamics of a process X after measure B. That's the key element here. So the Radon-Nikodym derivative, which is defined in Gears-Zenoff theorem, is used in Gears-Zenoff theorem, allows us to switch from measure A to B, and tells us exactly what is the step in between. The step between is Radon-Nikodym derivative. The first most fundamental process that we always deal when we talk about measure changes is, of course, the Black-Scholes model, so geometric Brownian motion, where you want to change measure P to measure Q. So in this case, we consider a stochastic process. So this is a geometric Brownian motion, where we have a measure P corresponding to the real-world measure. You can also see it because we have a drift mu. If we have a P and mu, essentially this implies that mu wasn't implied from the market. It is not calculated based on some arbitrage-free martingale properties, but typically means that mu was estimated based on some historical data, for example. Then we typically see then measure P as the measure under which the process is defined. In the course of computational finance, we discuss a bit more detail what is the arbitrage opportunities once we talk about measure P and Q. Here is the most important, of course, to see, okay, if we have a P here, typically this process is not a martingale if we discount it with the money savings account, because then this is associated with a different numeraire, or typically it's not even numeraire, it is just estimated from some historical data. In the world of Black-Scholes, we also have a money savings account. So already we have just mentioned it is related to the Q measure. So the dynamics, you can say, actually it's not really dynamics because we don't have a Brownian motion element, but in terms of D, when we talk about dynamics. So money savings account is defined in the following way. So we can actually see that this solution for this is that MT is equal to MT0, and then we have a times, and then here we have RT. So this is the solution for this ordinary differential equation. Okay, so what we can do right now, we can directly apply Gears-Zenoff theorem. So first we derive Nikodym derivative, and then we apply the Gears-Zenoff theorem to change measure. This is basically what we have just seen in the theory. What we can also do as an alternative is to impose or use the martingale properties and also properties of numeraires to change the measure of the underlying process. So here, this is typically a preferred choice, and also it's very intuitive how you go about. So what we know is that under the risk neutral measure, every quantity has to be martingale. So every quantity is divided by MT, because S will be expressed in units of MT. This quantity has to be martingale. So of course, first thing, if we talk about martingales, is to find dynamics of this quantity. So what we do, we apply ethos lemma to the quantity S divided by MT. So if we apply the ethos lemma, then here we see we have a 1 over MT dst. Then we have, so this is derivative with respect to S. Then we have a derivative with respect to M. And of course, we have also, second derivative with respect to S is just 0 because it's gone. Second derivative with respect to M. And then also we have a mixed derivative. Of course, we know also ethos table, where we know that dt squared is equal to 0. So this means this term is 0. We also have dwt is equal to 0. So this would be also implying this is equal to 0. And for the rest, we don't have any other terms there. So what we do next, we arrive on this those three terms. So d, the dynamics of the ratio of the s over mt is equal to the dynamics of s, we have the dynamics on t. So of course now what we have to do, we have to substitute this dynamics here. Right? So we have substitute the dynamics for s and substitute dynamics for m, and then let's see what comes out. Okay, after substitution, so we just directly, we are not talking about measure changes yet, we just apply Plato's lemma. We are searching for dynamics of this ratio, and we just substitute the processes, corresponding processes for the money savings account and the stock. And this is what we have arrived. So after simplifying some terms, when often some terms will cancel out, like here, for example, you can see, and after cleaning a little bit, here you can see that we have a two terms for the drift. So we have this drift term, we also have here a drift term, and then we have a volatility part. So we have a sigma s over dw measure p. Now we can use some properties of martingales. So we know that s of t mt, it has to be martingale. This also implies that the dynamics of this term has to be driftless. Now we have, of course, we have some drift terms. So that's the problem, of course. We see that the dynamics supposed to have under measure Q will be driftless, but there are some drift terms. And we also know that under measure change, the volatility part does not change. So this means that if we change measure, it's not only that the drifts will be gone, but also our volatility component. So this is our volatility component. It's a whole term, sigma stmt. The whole volatility component will be untouched. So of course, this would be Q, but it's untouched. So what we can see actually is we know exactly what we expect. We know that our new process, so under Q measure, and Q measure comes because we have a money savings account as the numeraire, has to have the following form. So we know there will be no drift, so this is gone, and we expect this type of dynamics. So it's a sigma st and t dw. Of course, but still we didn't use any measure change. And because actually what is interesting is that because we have a dynamics of stmt under measure p, we also know the dynamics of stmt under measure q. And what is actually interesting is that because we have those two elements, we can merge them together, we can combine them together to find what was the measure transformation. This is actually the key element of this strategy. Because if we start with a numeraire, we know what the martingales are, we know martingales properties. If we impose all those conditions on all the assets in our economy, actually our economy here consists of two processes, stock and money savings account. If we put all those conditions together, this actually implies us the measure transformation, which will be equivalent with the Gears theorem. So okay, so we know that these two, they have to be equal, essentially. Right? So this is basically by equaling them together, we can find out what is the measure transformation from P to Q. This is what we do next. So you see, we take, maybe this is not proper numbering here. So if we take the equation, this equation for the dynamics of stmt, and this equation, we combine them together, then we end up with this expression. You see, many things will simplify because actually everywhere we have a st over mt. So essentially everywhere this term will cancel out. We can divide both sides of this equation of those terms. And then we end up with the following expression. So we, of course, we have this sigma in front. If we divide sigma out, then we see dwq. So it's a new Brownian motion under Riesz neutral measure Q is equal to the Brownian motion under measure P with some drift correction term. So you see that by imposing the martingale conditions on the assets that we know that need to be martingale, also using the property that we know that under measure transformation or volatility terms, they don't change, we can actually figure it out. So we can compute proper measure transformation. So what we have next to do, we of course now we have this stochastic process for S. What we can do, we can substitute this Brownian motion here. We can substitute for this Brownian motion in here. This is what we do here. So of course this will be dwq minus this drift term, and then if you simplify everything, we arrive at the stoch process after measure transformation under Q. And of course now the big difference here is that the drift is not anymore driven by the mu, which is estimated based on some historical data in the measure P, but it's driven by R, and this R corresponds to the money savings account, which is actually the drift from the money savings account for the process MT.